With number one, it tells us that we're lifting a 40 kilogram box. We place it on a shelf 2 meters up. All right, how much work did we do? Well, we know that work is equal to a force times a distance. So let's go ahead and go from there. Do I know what my work is? I don't, right? That's what the point of the problem is. Do I know what my force is? Oh, I don't, but I do know what my distance is. So there's my distance of 2 meters. So now it may look like I can't really do this problem, but let's think back to the forces unit. I've got a 40 kilogram box. Well, that is a mass, and I can assume that my acceleration is gravity, which is 9.8 meters per second squared. In this case, we're gonna end up with a work that we want to be positive, so we don't have to worry about the negative for acceleration right now, since we want to come up with a positive answer anyway, because we can't have negative work. All right, so now I know my force, right? 40 times 9.8, or in other words, my M times my A gives me 392 newtons, and that should be in newtons. So 392 newtons, that is my force. So now actually I do know my force. I knew my distance from before. Go ahead and multiply those two out, and we're left with 784 joules. That's how much work I did in order to lift a 40 kilogram box up 2 meters. All right, part B, what's the potential energy of the box? Well, in order to lift this box up, so let's say I've got my box and I'm lifting it up on top of a shelf. In order to get it up there, I must have to do 784 joules worth of work to get it up there, which means that it has a potential to release 784 joules of energy on its way back down. So it has a potential energy of 784 joules. Or we could plug it into the formula, PE equals mg H, and also get 784 joules that way as well, so conceptually or mathematically. Part C, if it took us 2 seconds to lift the box, how much power did we use? Remember, now we're dealing with time, and even though it does tell us that we're looking for power, anytime we see time, we're most likely looking for power. Not in every case, but most likely. All right, well, we know the formula for power is P equals W over T, right? P equals W over T. We've got our work from before, right, from part A. That's where I'm getting this 784 from this part up here. Or conceptually, realize this potential energy of 784 joules we must have that because we did 784 joules worth of work to get it up there. So either way, that 784 is going to give us our work, and it tells us that we're dealing with 2 seconds. So remember to check your units. We're in seconds. Is it okay to be in seconds? Yes, this formula is in seconds. Work is in joules, and power is in watts or joules per second. So in this case, 2 seconds matches with 2 seconds that we need in the formula. 784 divided by 2 gives me 392 joules per second of power. Or remember, the other unit instead of joules per second is also watts. So it could have also been 392 watts of power. All right, part D. If the box fell from the shelf, how much kinetic energy will it have, or can it possibly have up to? Well, if it's falling off the shelf, so let's say it's up on our shelf and this thing goes to fall off the shelf, by the time it is just about to hit the ground, the moment before hitting the ground, it's going to have 784 joules of kinetic energy, because all of the potential energy that it did have is now going to be released. And as it's being released, it's going to be converted into something else. Well, the other something else, in this case, the other type of energy that we're dealing with is kinetic energy. So not to be confused with, they're both the same. It's not that they're both the same. It's that potential energy at the top is 784, or at its max, and our kinetic energy is at 0. On the bottom side of things, though, it's reversed. All of our energy has been converted into kinetic energy, and our potential energy at this point is 0, or at least very, very close to 0. We're assuming it's like right before hitting the ground. All right, last, at its peak KE, how fast is it going? Well, we know that the kinetic energy formula is related to 1/2 mv squared, so that's where we're getting this work from up here. We know that we've got 784 joules of kinetic energy. 1/2 is part of the formula. The m is 40, that's what we have from up there, and then we're solving for v squared. So when you do 784 divided by 20, you're going to come out with a large number, but that's v squared. We got to make sure that v squared, we end up taking the square root of that to get this answer of 6.26 meters per second. That would be our velocity. The other way that we could do this is rearrange the kinetic energy formula, right? Because what we could do is say, well, I want this half gone, so let's multiply that by 2 because I'm trying to get v squared by itself. So if I do it to one side, I've got to do it to the other. So now 1/2 and 2, that cancels. So I'm left with 2ke equals mv squared. Well, if I'm still trying to get v by itself, let's divide both sides by m now. So we're left with v squared. I'm going to go over to the other side here because I'm kind of running out of room. I'm left with v squared equals 2ke over m. But if I want to get v by itself, I got to take the square root of that. If I do it to one side, I've got to do it to the other. So we could rearrange the formula to v equals the square root of 2ke all over m. So it's another way that we could do it algebraically without having to worry about solving for variables later. We could sort of pre-solve for it, so to speak. All right, so let's see what we got up next here. Problem 2, if you say something has twice the power, what does it mean? There's a couple of different answers. Well, if we look at the power formula here, how could I get this to double? Well, if I want to get that to double, there's a few things that I could do. Could multiply my work by 2, and then I'm going to end up with twice the power. So in other words, like Miss Mardoyan has here, double the work. Right? If I double the work, then I'm going to end up with twice as much power. The other thing that I could do is cut this time in half. Right? If I cut the time in half, I'm still going to have a relationship of twice as much power that way as well. All right, number 3. How much work does it take to stop a 2,000 kilogram car that's going 250 meters per second? There's a couple things that we need to know. First of all, we need to know how much energy the car has, because if we know how much energy it has, then we know how much work it's actually going to take to stop it. All right, so do I know how fast it's going? I do. Do I know its mass? So now I can figure out its energy. There's a couple ways that we could figure out its energy. It is moving, so I should know that I'm going with the kinetic energy formula, because if I'm trying to stop the car, it must mean that it's in motion to begin with, and kinetic energy is energy that's in motion. All right, so that's the first way. So let's take a look at that. So I know my formula again is Ke equals 1/2 mv squared. We know v, that's where this 250 is coming from. It's squared because of the formula. I know my m, and the 1/2 is part of the formula. So when I multiply, what I would recommend actually first is doing 250 squared, then multiplying by 1,000, which is 1/2 of 2,000, or do 250 squared, find the answer, multiply by 2,000, and then divide everything by 2, or multiply everything by 1/2. Either way, you're going to come out with this really big number in your calculator. It's actually probably going to look like 6.25 something E7. But we want to round off to a couple of decimal places, so we should be left with 6.25 times 10 to the 7th joules. Because remember, kinetic energy is in joules. Well, in order to get this thing to stop, I'm going to have to do that much work in order to reduce my kinetic energy. Because again, work is a force over a distance, so I'm going to have to use this many joules of work, however that is, either from a huge force and a really small distance, or a very long distance and a small force, or sort of a combination of the two, going back and forth. But regardless, I'm going to need that much work in order to get this much energy to reach 0. And again, 6.25 times 10 to the 7th is a really big number, which is why we would normally use scientific notation from it. for it, sorry. Or you could have used 62,500,000 joules.